Okay, so last time we explored the Bremsstrahlung radiation. In particular, we focused on the physically interesting, realistic case of thermal Bremsstrahlung, in which the population of electrons is described by a Maxwellian. What I didn't say, and this is the comment I'm just about to make, is that we didn't consider relativistic electrons. So the corresponding emission is, of course, relativistic Bremsstrahlung. This is also an interesting case in some contexts, particularly in astrophysics. I'm not going to show that because I have to make a choice. And in any case, if you are really interested to see that, you can you can have a look at the Ribicki-Lightman textbook, in which there is also some instructive procedure of how to calculate that. The trick is something that we will be using also in other contexts, which is move to the comoving electron frame, work out the calculations in that frame, and then to get your results in the lab frame, you just apply what we've seen concerning how the different quantities just change. So this is a trick which is, when dealing with relativistic particles, is used repeatedly. So this is just a comment. Talking about the emission of the electromagnetic emission of relativistic particles, today we started talking about probably one of the most, if not the most important example possible about radiative processes, not only in astrophysics, which is synchrotron radiation. So what is that? Well, to have synchrotron radiation, first of all, the main ingredient, in addition, of course, to charged particles, is magnetic field. So let's suppose we have a homogeneous magnetic field, homogeneous just to make things easier. So you see here in this figure here, so all these magnetic field lines. As a matter of fact, when you have a charged particle moving within an environment in which you have magnetic field, automatically, because of the Lorentz force, the particle is accelerated. And by now, you know, you have emission of the particle. Now, it's interesting to distinguish between different cases. So let's consider, first of all, the non-relativistic case. So you have electrons, non-relativistic electrons, so beta much smaller than 1, moving within the magnetic field. Of course, you have that, you know very well from your previous courses, that you have a kind of helical motion of the electron around the magnetic field lines with a given frequency, which we will see is called cyclotron frequency. And so you have essentially, you as observer, you see the electromagnetic field. In particular, let's focus on the electric field. If you think of the Poynting's vector, so you have an electric field which will be changing just with a given period given by the cyclotron frequency. So as a matter of fact, the radiation that you will get mostly depend on this frequency. So we'll be focused on that frequency and then possibly on some of its harmonics. We will see that. Things change significantly instead when, from a non-relativistic case, you move to a relativistic or ultra-relativistic electrons. In that case, the emission, well, from a qualitative point of view, you have still the electrons are accelerated by the magnetic field. So again, emission. But what we'll see is that in that case, the properties, in particular the spectrum, so how energy is distributed over frequency of the resulting radiation, has a completely different look, has a completely different dependence on frequency. So the radiation emitted by ultra-relativistic electrons in the presence of magnetic field is called synchrotron radiation. So the ingredient, the first thing to know is, what are the ingredients for synchrotron radiation? Magnetic field and ultra-relativistic charged particles. I keep saying most of the time electrons because as I'll show you, and as we already saw also in the case of Bremsstrahlung, electrons, thanks to the combination of charge and mass, are the most efficient particle, radiating particles. But of course, the same arguments that we will see just apply equally for any charged particle, even if, okay, the most interesting cases are about electrons. So let's see exactly, let's study the dynamics of an ultra-relativistic electron. So we just apply here, of course, the second law of dynamics, taking into account that you have the linear momentum is refers to a relativistic particle, so it's gamma mv, and equal just the Lorentz force, just like that. I remind you, this is Gaussian system. We make an assumption. We assume that the modulus, the magnitude of velocity, changes very, very slowly. In particular, after one loop of the electron around the magnetic field line, the modulus of the velocity, we neglect the change. Okay, so having said that, of course, gamma, which just depends on beta, so it just depends on the modulus of v, is we can approximately treat it as a constant quantity. So we just take it out of the derivative. So this is the equation. Now, if you simply rearrange in a very simple way this term, so you find the acceleration of the electron as a function of, you see, here I put the minus sign because I swapped the two terms of the vector product. So you know this is anticommutative. So you can swap the two terms at the price of changing sign. That's exactly what I did. And in particular here, among brackets, I put a quantity, which is QB over gamma MC, and I called it omega B. Well, if you remember, well, one of the very first things that you've learned about derivative of vectors, you know that when you have the derivative of something, of a vector, which is something, one vector time vector, the vector itself, it means that the derivative is perpendicular to the vector itself. And in particular, this guy is an angular frequency with which the vector itself, in this case v, just rotates as a function of time. In the case of angular momentum, if you remember, this is just a precession of angular momentum. In this case, we have v. So v is just a vector which changes direction, keeping its modulus constant, changes direction according to this angular frequency, which is omega b. Omega b, it's called gyration frequency for obvious reason that you can imagine, just because it describes the frequency, the angular frequency with which the velocity of the electron is just rotating. And there's also another useful definition, which is exactly what you all should be already familiar with, which is in the non-relativistic case, which means when gamma is 1, so when the electron is non-relativistic, the gyration frequency is also called cyclotron frequency. It's the frequency, or Larmor. L here as a subscript stands for Larmor frequency. The idea is the same. So, having defined the Larmor or gyration frequency, well, gyration frequency taking into account the possibility of an ultra-relativistic electron, you immediately see that the acceleration, the modulus of the acceleration is, well, getting back, you see from the vector product is just the product of the two magnitudes time the sine of the angle between them, which here in terms of vector, the angle is this guy here. So either you take the modulus of v sine alpha, we will see that we call this angle alpha, or just the perpendicular component of the velocity, because this is the sine of this angle. So v sine is nothing but v perpendicular. So the acceleration is that, the modulus of the acceleration is that. And of course, the acceleration is directed perpendicularly to the field lines. So it's directed here toward the central point that lies within the magnetic field lines. And this is the motion that you already know from your previous studies. Now, we know the acceleration. Let's assume as I said, talking about synchrotron radiation, we assume the electron or the charged particle is indeed ultra-relativistic. So if we want to calculate the total power emitted, lost by the charged particle, it's just a matter of using Larmor's formula, of course, paying attention to the relativistic case. So it's important, if you remember the formula, the relativistic formula of Larmor, it's important to understand both components of the acceleration with respect to velocity. So in this case, the acceleration is just perpendicular to the velocity itself. So all the acceleration that we calculated is just, it's entirely perpendicular to the velocity, which means that if you remember, you had gamma 4 times this guy here plus gamma 6 A parallel. We have no A parallel, so it's just this one here. You see that compared with the non-relativistic version of the Larmor's formula, you have a gamma to the 4th power. This is really huge dependence on the energy of the electron. So just merely replacing into the Larmor's formula the value for the acceleration that we have in this case. So given that it comes with a square, so you have all this term here squared. So you gain, in particular, b squared over gamma squared, mc squared, and v perpendicular square. So just you see that you end up with a dependence on the square of the magnetic field, the square of the Lorentz factor of the electron, as well as this term here, where here I put just v over c as beta perpendicular. And this is the power of one electron with a given velocity, with a given angle. Again, this is a reminder why I keep saying sometimes electrons, because if you compare again, if you imagine you have both one electron and one proton just traveling within the same, having the same Lorentz factor and traveling within the same angle within the same magnetic field lines. So if you compare the power lost by the two particles, you immediately see that the dependence of 1 over m squared again tells you that the radiation emitted by an electron will be 4 million times greater than that of the proton. That's why if you have a plasma, for example, of just filled up with protons and electrons, you can easily neglect the power. There is power. So if, for example, if one asks you, well, do protons emit through synchrotron radiation? Of course they do. But as a matter of fact, you can, when you have both protons and electrons, you can neglect the contribution of protons that you make a very, very small approximation, a very accurate approximation anyway. So this is also important to remember. If we rearrange, so the formula of the total power emitted by the particle by multiplying and divided by 4 pi, that's exactly what I did, and by dividing and multiplying by c, so you see that among square brackets, here I have something that should look very familiar to you. This is indeed sigma Thomson cross section. So the Thomson cross section. So, okay, this is just the definition of alpha. So the angle between the velocity and the magnetic field line, I called alpha, as I was saying before. And this is a name, this pitch angle. So the pitch angle is the angle between the velocity of the charged particle and the magnetic field lines. Okay, so b perpendicular, as I said, is just beta sine of the pitch angle. And you see, this is really, so rewriting the total power lost by the electron as a function now using the Thomson cross section is particularly meaningful if you look at this formula here. And it is even more so if, for example, look, you have b squared over 4 pi. If you remember the energy density formula of an electromagnetic field, in this case we just have magnetic field in the lab frame. So b squared over 4 pi, if you divide and multiply by 2, b squared over 8 pi is just the energy density associated with the magnetic field. So what I called here capital UB. So UB is energy density associated with the magnetic field. So energy per unit volume. So now let's have a look at this formula. You have that the total power emitted by the electron, so energy per unit time lost by it, is energy density times the velocity of the electron. The velocity should be beta c, but as a matter of fact, we are talking about ultra-relativistic electrons, so is essentially c. So c UB, velocity times energy density, if you remember, is something that I told you, oh, this is very general stuff that we encounter, we meet in several contexts. So velocity times energy density is just energy flux. Energy flux times an area, which is the Thomson cross-section, is indeed energy per unit time. So you might look at the power lost through synchrotron emission of an electron, of a charged particle, as the flux that is just kind of crossing the particle itself, time its cross-section. Here we are talking about, of course, interaction between electromagnetic fields and particles. So again, the cross-section that comes into play is Thomson cross-section. So it's very useful here because you give it a physical interpretation which is really useful. And what is important here to remember, if you don't remember the coefficient, okay, never mind. What you should nevertheless remember is the dependence of the Lorentz factor. This is really important. So you see there is a square dependence. You double the Lorentz factor, the synchrotron power gets 4 times larger. So the dependence on gamma squared, first of all, is very important. The scaling with the energy density associated with the magnetic field is proportional. And of course, the sigma Thomson. This is, as far as I'm concerned, this is what I would like you to remember. Then if you remember the coefficients, well, the better so, but it's not crucial. Oh, let's mind, this is for a given, you have beta perpendicular, so beta sine alpha. So this formula, it refers to a specific pitch angle. You can wonder, for example, let's suppose you have a population of electrons randomly, or better, isotropically distributed, which means every possible direction is equally probable to any other possible directions. So it means that alpha can have any value with the same probability. So if you work out, let's suppose the average power emitted by, of course, if you have an electron which is traveling parallel to the magnetic field, is not accelerating. So in that case, you have no synchrotron emission at all. And indeed, if alpha is 0, the power is 0. While of course the maximum case will be when is moving right exactly perpendicular to the magnetic field lines. So you can average out, assuming an isotropic distribution. And what is to be done? Assuming so that all of them have the same Lorentz factor, what only changes is the pitch angle. So it's just a matter of calculating the average value of the only thing in here, which depends on the pitch angle, which is beta perpendicular. So beta square is just the same for all guys, so you can just take it out of free integral. And again, you have integral over the entire solid angle of sine square. I'm sure by now you're already bored by this, you already know it. We saw many times, it's 8 pi over 3. So 8 pi over 3 over 4 pi, it's just, you just gain a factor of 2/3 essentially. So 2/3 beta squared. So replacing into that, here the average, so this average here, it's an average in the sense of averaged out over the entire isotropic population of electrons, okay? So of course you have electrons that are emitting a lot and some others that are emitting very few, but this is the average power. emitted, which again, this is probably easier to remember. I don't know. So again, what I would like you to remember is the dependence of the synchrotron power on the Lorentz factor, as well as this, of course, on the magnetic field energy, as well as the Thomson cross-section. So this is all about the total energy lost by the electron, no matter about the spectrum. So the spectrum, we mean how instead all this energy is distributed as a function of the frequency of the emitting radiation. Well, this is very important to understand, and this is going to take us quite some time, I would say, but it's really worth it, because we see how relativity, special relativity, changes things with respect to the non-relativistic case. So to remind ourselves of what we've learned about what changes in terms of the emitted radiation in general by an accelerating particle when we move from the non-relativistic case, which is what you see here on the left. So in this case, you have a non-relativistic electron, which is being accelerated with the acceleration is entirely perpendicular to the trajectory. Indeed, this is indeed the case. So we see that, I remind you, we saw that the pattern as a function of direction is just this sine square. Well, the angle is the angle between, of course, the acceleration and the line of sight of the observer. And we see this in this case because acceleration is perpendicular to the trajectory. If the only thing we change is that it's just the Lorentz factor, so we move on the right panel. In this case, the electron is still accelerating in a perpendicular direction to its velocity, but now the Lorentz factor is much larger than 1. So we saw, and we call this relativistic beaming, that most of the energy is just emitted within a cone whose semi-aperture angle is 1/gamma. So the higher the gamma, and the narrower the cone along within which the cone is, of course, centered on the direction of the velocity itself. So if you imagine you are an observer receiving radiation from these kind of electrons, you see that things can just relativity has a strong impact on the kind of signal that you receive, and then we will see in a moment in more detail what I mean. So let's suppose we see we are here on the right. So this is our eye, our detector. So this is a piece of trajectory of the electron, okay? And here I showed the cone of the relativistic beaming of the electron in two particular instants. In this case, so let's suppose the electron is moving this way, as you can also see from the velocity vector of the electron. So when the electron is here, it means that if you look at the line of sight pointing towards you and the relativistic beaming cone, at this point here, when the electron is here, you don't get any radiation. When it is here, you start seeing, because the line of sight enters the cone of emission, the cone within which most of the radiation is emitted by the electron. And you keep receiving radiation as long as the electron lies in this piece, in this arc. Finally, your line of sight exits this cone when the electron is right here, because you see the line of sight now coincide with the other boundary direction. So it means that throughout all the trajectory, this is a projection, of course, you will get radiation only emitted by the electron within this interval. Other than that, you are just out, your line of sight is out of the emitting cone, so you are not going to expect to receive any radiation. You say that this is very important consequence of the relativistic motion, because in the absence of relativistic motion, you don't have this cone, you don't have any relativistic beaming, so you should receive, of course with different intensity, but you should receive radiation at any time, essentially, according to the sine squared theta that we already saw. So let's focus on the geometry of this stuff. So I call delta theta the angle subtended by this portion of the trajectory. Okay, and again, from simple geometric considerations, you see that this is just nothing but twice this angle here. This angle here is the semi-aperture angle of the beaming cone. So this is 1 over gamma. So delta theta is just twice as large. So 2 over gamma, just like that. Now, let's call A as the radius of this. Well, A is nothing but the curvature radius. So it's the radius of the circular trajectory that is instantly described by the electron. So please make sure you're not confused. I'm just following the notation of Ribicki-Lightman. So make sure you're not confused. A is no acceleration. A is just a curvature radius. Okay. So just the relation if delta S is just the length of this arc here, well, of course, this is nothing but the subtending angle times A, where, of course, it's implicit that delta theta is meant to be in radiant units. Otherwise, this wouldn't hold, of course. So this is, of course, 2A over gamma. Now, the goal here is to find, in particular, the curvature radius as a function of the dynamic quantities that we obtained in the previous slide. So here is just v, the velocity of the electron, as you know, from uniform circular motion, is just the change. If I call the corresponding change of the velocity between here and here, this is just v times delta theta for the very same reason. So delta S is also v times delta t. So you can express delta t as delta S over v. Now let's consider the modulus of the equation that we saw before. Okay, this is just second Newton's law applied to the guy we already saw. Now, delta v over delta t, if you replace delta v as v delta theta and delta t as delta S over v, you have this guy here equal to this guy here. I just replaced, of course, instead of the modulus of this vector product, just the two products, VB times the angle, the sine of the angle between them. Instead of going through all this, if you remember from kinematics, from basic kinematics, you could immediately see that this guy here on the left-hand side of this equation is just v squared over the curvature radius. And you know that v squared over the curvature radius is just the normal component of the acceleration. And indeed, delta S over delta theta is indeed A. So is indeed the curvature radius. So v squared over curvature radius is just the modulus of the acceleration. In this case, as I said, the acceleration is completely perpendicular to the velocity. So just the modulus of this guy. So you can just easily skip all these passages and get straight away to this point. Now, again, remembering that the curvature radius is nothing but delta S over delta theta. So replacing this guy here, you bring v squared on the other side. So here you have v over v squared, you are left with 1 over v. So 1 over curvature radius is this guy here. But if you remember the definition of the gyration frequency, it was indeed QB over gamma MC. So if you work out the reciprocal of both sides of this equation, here you have 1 over A, so it becomes A. And here you have gamma MC over QB, which is 1 over omega B. And here, of course, you have to work out the same. So now what we have is the curvature radius as a function of the velocity and the gyration frequency, and also in addition to the, of course, the pitch angle. Now, A, what is A? A is also, if you look at here, A, you bring 2 over gamma on the other side, so you can express also the curvature radius as a function of delta S. So by equating these two equations, expressing the curvature radius in two different ways. So this guy equals this guy. You immediately have delta S. So the length of this part as a function of the dynamic quantities which describe the motion of the electron in addition to this guy. Oh, by the way, I didn't say that. I assume, and this is indeed the case, if you think gamma in the ultrarelativistic case is large, so this angle is small, which means that delta S is small. So I implicitly assume that delta S is a straight line. So we are talking about small angle here. I didn't show as a small quantity just because of the clarity. Otherwise, the figure wouldn't be clear enough. But we can clearly assume that this angle is small, so this is also small. So you can just assume that this delta S arc is a straight line. Okay. Now, let's give some names. Let's assume we consider two photons. We call photon 1 and photon 2. Photon 1 is emitted here when we begin receiving radiation from the electron. So, and we call T1 the emission time of the first photon that you will see in just one loop, emitted by the electron. Mind that T1 is the time measured in a fixed frame. So in this frame, the only frame I'm referring to so far. And in a symmetric way, we call T2 the emission time of photon 2, where photon 2 is the last photon emitted that you receive. So at T1, photon 1 is emitted here and will be traveling towards you. At T2, photon 2 is emitted here and will also be traveling towards you. Now, okay, here I just copied what I already obtained. So I know delta S, so the path that has to be traveled by photon 1, but which has not to be traveled by photon 2, because when photon 2 is emitted, the electron has already moved here. So now the goal is to derive the time interval between the arrival time of photon 1 and the arrival time of photon 2, which is exactly what you measure, you as an observer. What you measure, so if you think the time interval between the emission of the two arrival times tells you the duration of the pulse of electromagnetic radiation that you receive in one cycle. So that's why it's important, because once we know the duration, we know how the measured electric field of the electromagnetic wave associated that we receive varies as a function of time. But once we know that, we can move to the Fourier transform and work out the spectrum of the radiation. So that's the goal. So let's work out first the time interval, not in the arrival time, in the emission time. Well, in the emission time, it's just T2 minus T1. Well, this is just the time it takes for the electron to move from position 1 to position 2. So just delta S over V, the velocity of the electron. Easy. Everyone can immediately realizes this. But delta S is just 2V over gamma and B, all the stuff here. So if you replace this here, you see that you end up with this value here. Now, let's call the corresponding arrival times, so the time at which they arrive at the observer, and to distinguish them with from the corresponding quantities, I put as a superscript a capital A. So A, of course, stands for arrival. Now, let's work the difference between the arrival times. If you think it's exactly the same difference between the two emission time, minus what? Well, you have to remove the time it takes for photon 1 to travel, the time it takes for a photon to travel delta S. Delta S, I remind you, is the path that one photon has to travel, but that has not to be traveled by the second one. The second one takes advantage of the fact that when it is emitted, it has already a bonus, kind of bonus. It has it has a shorter path. And how much short? Well, delta S. And in terms of light travel time, well, delta S over C. So you see, this is really important to consider. So of course there is this difference. But now, if you so delta T2 minus T1 is just delta S over V. So if you collect delta S over V, this guy is just 1. And the second term, the one you subtract, you can express as minus 1 minus beta. Now, okay, let's replace delta S over V as this guy here. Over V, so this guy here. Now let's focus on the term among brackets. 1 minus beta. Well, this is interesting. This is really small. Why? Because beta is very close to 1, because we are talking about ultra-relativistic electrons. Now, what is convenient to do is just to Taylor expand beta. In particular, beta, I remind you, is a square root of 1 minus 1 over gamma squared. So if you Taylor expand beta, you get this term here. So 1 minus beta. How we know that it is small, but now we can express how small it is as a function of the Lorentz factor. 1 over 2 gamma squared. So replacing into that, you see that the arrival time interval is hugely diminished by a factor of gamma squared, because here you have something of the order of 1 over gamma, and here the same thing, apart from a factor of 2, 1 over gamma squared, shorter time, 1 over gamma squared times shorter. And this indeed, if you think from a qualitative point of view, this is indeed the case, since what happens is that the electron, soon after it emitted photon 1, the electron is traveling at a speed which is very close to the speed of light. So it's kind of chasing the photon that has just emitted. So when it is time for the electron to emit the second photon, it is relatively close to photon number 1. See what I mean? So that's why the two photons that are traveling towards you are much closer. So you receive them with a time interval comparably short. Now, if you think in terms of frequency, again, exploiting the duality between time and frequency, you have a time interval delta T A. So the corresponding frequency is just 1 over in terms of angular frequency. So there is no 2 pi factor. So delta omega, the corresponding delta omega, when you move to frequency domain, is just the reciprocal of this guy here. So gamma cube times the gyration frequency. So we conveniently define a so-called critical frequency, which by definition is exactly what we see delta omega, except for a factor of 3 over 2, which you can just, well, you have to remember, but it's not important to understand why. Just the important point is to see the dependence and pay attention to this. So the critical frequency is something which gives you the scale of the spectrum of synchrotron radiation emitted by an ultra-relativistic electron or charged particles. It's important to remember how it scales with gamma, but pay attention. Here, the formula here, the definition of critical frequency might confuse you. Why? The dependence is not with it, the scaling is not with gamma cubed. But if you remember omega b is QB over gamma MC. So pay attention. Do not be fooled by this. The scaling of the critical frequency with the Lorentz factor is with gamma squared, because omega b scales as 1 over gamma. So the overall dependence of the critical frequency with the Lorentz factor is gamma squared. You have to know this. No way that when talking about synchrotron radiation, you don't remember how critical frequency depends scales with gamma. This is something that you have to know. Okay, so very, very important to remember this. Why is all this so important? Well, let's have a look at this figure, which describes what changes when we move from a non-relativistic electron to a mildly relative. So the non-relativistic electron is the top row here. The mildly relativistic case is when V is still smaller than C, but it starts being comparable with it. And instead, in the ultra-relativistic case, which is the bottom row, when so the first column shows you the pattern as a function of direction. So something which I already commented in the top here, in the non-relativistic case, and here in the ultra-relativistic case. So the middle case is something in between, of course, as you can imagine. So let's now focus on the middle column. The middle column tells you how the electric field of the electromagnetic wave measured by a generic observer varies as a function of time. So in the non-relativistic case, or when rather than speaking of synchrotron radiation, as I told you at the beginning, we can speak of cyclotron radiation. Well, as I said, you have no relativistic beaming, so you see radiation at any times. In particular, you will see the electric field just oscillating more or less in a sinusoidal way. But when you move from this to the frequency space, because that's what you are interested in now. So to study the spectrum, so how power is distributed over frequency, it's just a matter of calculating the what? Well, you have to calculate the intensity. So E squared, E modulo squared, and then you work out the Fourier transform of the modulo squared of the electric field. But this is just a matter of Fourier analysis. If you have one just component, well, most of the power will be just around one single line. And this line in the spectrum, the frequency is just the cyclotron frequency, okay? So very easy case. When the velocity begins, is no more completely negligible with respect to the speed of light. So you have a mildly relativistic electron. So for example, 0.2, 0.3, 0.4, 0.5 times the speed of light. So a fraction of the speed of light, but not so negligible fraction. You see that the shape of the electric field starts changing. And in particular, this is reflects to the pattern emitted by. And what this means? Well, it means that if you work out the Fourier analysis, Fourier decomposition of this guy here, you start seeing some higher order harmonics. So here you have the second harmonic. In the extreme case, when it becomes relativistic, you see that you have this strong pulse of the electric field lasting just how long? Well, delta TA, the arrival time interval that we just calculated. But we see that this scales as 1 over gamma cube, or 1 over gamma squared if I consider times omega b. So it means that for most of the time you don't get any radiation, or very, very small amount. That's exactly here. And sex for the bright pulse, when your line of sight is just lies within the beaming cone. So it means that you are just using up a lot of harmonics. And in the extreme case, we will see, because then these are not, these lines are somehow broadened also by some effects that I will comment in a moment. So we move essentially from one discrete spectrum, one single line, to a continuous spectrum. But not only is continuous spectrum, but also most of the radiation, we will see, is emitted at a frequency which is no more the gyration frequency, but it's the critical frequency. So that's the role of the critical frequency. The critical frequency tells you at which frequency you get most of the power emitted through synchrotron radiation. So here the effects, the most important effects when you move from cyclotron radiation to synchrotron radiation there are two effects. One, the spectrum moved from a discrete spectrum to a essentially continuous spectrum. And the second effect, that most of the power here is emitted at the cyclotron frequency. Here, most of the power, the peak of the power and so most of the power will be emitted around the critical frequency. And the critical frequency is kind of gamma squared times the cyclotron frequency. So completely different. And this is merely completely due to relativity, special relativity. Special relativity changes the pattern of the angular emission, and the beaming effect has a strong impact on this. So this is really beautiful. So when you are in between the two extreme cases, so when you consider, for example, the emission of a mildly relativistic electron, and in this case, mildly means that beta here, so V over C is just 0.4. So close to half the speed of light. So you have a lot of harmonics coming into play. So you are in the resulting spectrum is something in between the discrete spectrum, when you have the fundamental, a few harmonics, and the continuous spectrum of synchrotron radiation. Here you have, this is a log-log plot. You have the contribution of 20 harmonics. And if you wonder why these are not straight lines, but each of the harmonics are somehow broadened, this is due to the fact that this is the result of many electrons having all the same beta, but with slightly different pitch angles. So if you slightly change the pitch angle, of course, the critical frequency changes as a consequence. So you have just that explains why you have this kind of broadening. So due to the you change the pitch angle within the beaming cone of the end, so you have this broadening of the lines. But the effect is this one. So in here I called the gyration frequency, well, I should have called it the Larmor frequency. Gamma QB over MC is just the Larmor frequency, or the cyclotron frequency, okay? Well, so this shows you the transition between the two cases. And this is a beautiful example. This is real observations of a neutron star. So you see energy per unit area, per unit time, per unit energy. So it's energy density. So it's a specific flux, if you want, as a function of energy. Energy here is in keV, so hard X-ray, gamma ray, soft gamma rays. What is beautiful, this is a neutron star belonging to a binary system. You see that the spectrum should be a kind of cut-off power law, so something straight, which then just exponentially cuts off. You see this line just going up and down. If you work out the energies of these four features, you find out that these are the fundamental E1 and the second, third, fourth harmonics. Here they are not equally spaced just because this is a log-log plot, okay? So, but if you plot this linearly, you see that the spacing between the harmonics is the same, is uniform, of course. This is the result of the spectrum, which is resonant with the harmonics of what? Well, the interpretation, which provide a very good description, because you see the model fully describes this kind of oscillations. This is due to the magnetic field of the neutron star, in particular the magnetic field close to the surface of the neutron star, the region where the radiation is emitted. So the photons just are resonant with what? Well, with the magnetic field. So there is an absorption which is increased by this effect. But Look, if you measure the fundamental, in this case, the fundamental is around 13 keV. But if you remember the formula of the cyclotron frequency, in this case, you have to take into account that the radiation is coming out of the surface of an object with a strong gravitational field. So you have to consider the so-called gravitational redshift. So 1 plus ZG is nothing but the gravitational redshift. But let's forget for now this term. So the cyclotron frequency, which is the frequency of the fundamental line, is just h nu g, where nu g is just omega g over 2 pi. So the cyclotron frequency, but the cyclotron frequency is QB over MC. You see? So you immediately see that if you manage to measure the fundamental energy, so all these guys are quantity. The only variable one is the magnetic field intensity. So this is a powerful way to measure the intensity of the magnetic field of, for example, of a neutron star. So you can just have fun calculating it yourself, this value. If you replace the value of the cyclotron line, you see that you have something of the order of 10 to 12 Gauss, which is a tremendously huge magnetic field intensity. If you remember, in terms of Tesla, this is 10 to 8 Tesla. I remind you that the most intense fields that we can reproduce in the lab are kind of Tesla. I don't know if something more, but not orders of magnitude greater than 1 Tesla. Here we are talking about 100 million times more intense. And if I have time in the future classes, I will show that there are neutron stars whose magnetic field can be as high as 10 to 15 Gauss. So really, really mind-boggling objects. So if you want to study the physics of these objects, of what happens in the fundamental physics in the presence of such large magnetic field, there's no way you must look at the universe, in particular this kind of objects. So this is a really fantastic way to measure the magnetic field, just interpreting what you see as the result of the resonant, as the resonant cyclotron lines. So this is a beautiful example in which you see the result of the emission, in this case of absorption, of mildly relativistic electrons in the presence of a huge magnetic field. The gravitational redshift, you will know more if you attend the course in general relativity, but essentially you can see that you can imagine from a point of view of conservation of energy, when a photon is escaping from a huge gravitational potential, well, you know very well that when you are just escaping the gravitational potential, well, you have to pay energy. In this case, the photon loses energy, but if you think of a photon's energy, when a photon loses energy, it means that it becomes redder, okay? So that's why redshift. So it takes into account that. But apart from that, and in the case of a neutron star, that's really important to take into account. Okay, this is now the point I wanted to make, just to make sure you're not confused by this. So let's move on. Let's get back to the ultra-relativistic case. So when you have an electron which is moving with a given pitch angle alpha. So alpha is the angle between the electron's velocity and the magnetic field lines, which here are shown as horizontal lines. So you immediately see that the velocity of the electron just describes this cone. Just think of the velocity. Velocity always keeps a constant angle, the pitch angle, with the magnetic field lines. It just rotates according to the surface of this ideal cone. Well, this is called velocity cone for obvious reasons. But now, if you think of the directions of where most of the radiation by this specific electron is emitted, well, you have to consider that electron emits most of its radiation close to its velocity within 1 over gamma angle, the beaming, relativistic beaming. So if you imagine to project this cone, it means that unless To receive a significant amount of radiation, synchrotron radiation, your line of sight has to lie on the boundary of this cone within 1 over gamma angular width. Okay, if you are out of this kind of corona, well, you are gonna get very a very small amount of radiation, if not anything. So this is something very important to take into account. And again, this is, you see, all this is a consequence of special relativity. Beautiful. So let's get back and I showed you a few slides ago, I showed you in a qualitative way why when moving to synchrotron radiation, the spectrum becomes continuous. But I didn't show you, for example, well, I didn't prove it yet. And in particular, I haven't proven yet why most of the power is emitted around the critical frequency. Now let's see this. This is going to be quite mathematical, a little bit of algebra and mathematics, but it is important to see at least once in a lifetime. So the electric field as a function of time is what we measure as observer. Okay, but if you think of the drawing of you remember the arc delta S I designed as a function of theta. Well, it means that essentially, if theta describes the angular position of the electron along its orbit, it means that the electric field is a function of time. Time will be a function of theta in which units? Well, what matters in this case is the beaming angle, the relativistic beaming angle, which is 1 over gamma. So the dependence will be, of course, the flux, and so the electric field will depend on theta, so on the position of the electron, but in units of, on the angle theta, measured in units of what is the scaling angle, 1 over gamma. So the ratio between these two angles, theta over 1 over gamma, is just their product. So it will be a function of the product of gamma times theta. But now let's think of this, of what we already seen. The time, the arrival time, here I didn't put TA because this is the only time now we are working with. But T, the arrival time is, if you remember, delta S over V, here delta S is just S. I just assume to measure the position along the arc of the electron just from a starting point, a generic starting point. So this is a formula we already obtained. S over V, so the arrival time is a function of the point, of the position S of the electron along the trajectory. So you can express S as a function of, just you just bring all this stuff on the other side. So it means that you also remember that the central angle, the subtending angle by the arc S, is just S over A. Well, A is the curvature radius, I remind you. So again, by replacing S by Vt over 1 over beta, this is just the angle. Now, the goal, what is the goal here, is to turn this argument into a function of time, because this is the final goal. We want to derive how the electric field depends on time. Once we know that, we can calculate the spectrum moving from the time domain to the frequency domain, just in terms of Fourier transforms. So that's the plan. So gamma theta now is gamma times all this quantity depending on time. Okay, so I just replaced here, instead of theta, just this guy here. But again, 1 over beta, I remind you, is 1 over 2 gamma squared. So 2 gamma squared gets to the numerator, so you gain a factor of 2 gamma cube V over A. But look, V over A, again, the velocity over the curvature radius is something that we obtained when we calculated the curvature radius, is just omega B sine alpha. But look, here we have gamma cube omega B sine T. If you remember the definition of critical frequency, that's exactly, apart from a factor of 3 over 2, but here we don't care, we just look at the proportionality of the scaling, This is just the critical frequency. So we obtain that the product of gamma times theta is nothing but omega c, critical frequency, times time. T, I remind you, is the arrival time, is the time that matters to you as an observer. So it means that the dependence of the electric field that you measure is on time is in a specific way. So it depends on time through the combination, through the product of critical frequency, time t. You cannot have t on its own. So the dependence of the electric field goes through this product, which is an dimensional quantity, or it is an angle if you want. So now we are in the position to work out the corresponding Fourier transform of the electric field. So this is just, I don't care about the numerical coefficients. This is just a matter of what I care is the dependence on frequency. But again, you are calculating the Fourier transform of something which depends on time in a very specific way. Here by G, I denoted that whatever function. I don't care now. What I mostly care is the temporal dependence goes through this product, omega c times c. So by changing variable, I define this new variable psi as this guy here. So you immediately see that the dependence on omega, if you multiply in the exponential argument just by multiplying and divide by omega c, you immediately see that you have this guy here. But that means that now let's remind ourselves what the power that we measure depends on. Well, as I said, well, the power scales with intensity. So in particular, when we move to the frequency domain, it's just the modulo squared of the Fourier transform of the electric field, E tilde. So the power, I remember, this is dW over d omega, d capital omega, which means energy per unit frequency per unit solid angle. We want power, so we want this guy time averaged. So given this is a periodic motion, we just divide all this, we integrate in the solid angle. We want to calculate the entire energy lost by the electron per unit time. So we just divide by the period. So this is the average power emitted by the electron. We can think of it as just dW over d omega, so the power just over time. And you immediately see that given that this scales depends on E tilde square, you see that the dependence on omega gets through the ratio between omega and omega c. So whatever the mathematical function that describes this dependence is, the dependence of omega goes through this ratio. Okay, this is really important. So f is a dimensionless function, and c1, yes, is a constant that has to take into account that normalizes the total power emitted. But here, the point I wanted to make is to find out, and that's exactly our result, how the spectrum, so energy distributed over frequency, depends on frequency. And we see that it depends through this ratio. So it means that if you change omega c, provided that you look at the value of n omega giving you the same ratio, the power will be the same. But look, if I integrate the spectrum of synchrotron radiation over the entire frequency range, so from 0 to plus infinity, I get the total power emitted by the electron. Okay, on one side, I just use the formula I've just come up with. So I know that this is a function of this ratio. But if you remember what we've just seen at the beginning of this class today, when we exploited Larmor's formula, I said, well, when you use Larmor's formula, of course, this is useful when you want to calculate the total power and you don't care the spectrum. You don't care about the frequency, the dependence on frequency. So this result is something that we already calculated. Okay, this is another mathematical passage in which you redefine the integration variable. So you see that you have x, which is an undimensional quantity, so the scaling is just with omega c. But we know the result. And indeed, this result that I put here is the formula we've come up with that we obtained applying the relativistic Larmos formula for a given electron with a given Lorentz factor gamma and a given pitch angle alpha, if you remember. If you get back to the first slides that I showed you today, that's exactly. So we demand that has to be satisfied. But this automatically determines the value of the C1 constant. So the C1 constant is just that. And remembering, here I remind you the definition of the critical frequency, just by making it explicit, the omega b. And so you clearly see the square, the dependence, the scaling with gamma square, as I said. By replacing the value of omega c here in the denominator with this value, you see here in particular that the dependence on gamma just cancels out. In particular here, b squared over b, you are left with b. Here you have q to the fourth power over q, so q to the cubed, and sine square over sine, just sine. And what I didn't tell you is the nature of this capital F function. This is a function of an undimensional quantity, and it is defined in such a way that the total power, you have a slightly change in the numerical coefficient. Well, that's depend merely on the way this capital F function is defined. But apart from that, you see that the dependence on the physical quantities is just, of course, the same. So in particular, the dependence on the charge, on the magnetic field, on the pitch angle, and on the rest energy of the particle. So this is the formula that tells you the spectrum of one single electron with a pitch angle within the emitting synchrotron radiation within the magnetic field. You might wonder, oh, where is the dependence on omega? Look, it does depend on omega, but not in a so explicit way. You have to remember that the dependence on omega goes through the argument of this f function, because omega c scales with gamma squared. So that's where the dependence on p omega on gamma comes from. So don't be fooled by this. In particular, for your information, I must tell you that this capital F function, if you die for knowing exactly what is this function, well, this is by definition this formula here where capital K is the modified Bessel function of order 5/3. This is just for your information. And this function peaks when the argument is about 0.3, so 0.29. It is interesting and it is important to know the two asymptotic regimes of this function. In particular, this capital gamma is the gamma function. And look at the dependence on the argument. It scales when the argument is much smaller than 1. So if you look here, it means in terms of frequency, when you are considering the energy emitted at frequency much lower than the critical frequency, this behaves like a power law with an index of 1/3, x to 1/3. So it's a power law with 1/3, 1/3. Well, in the opposite regime, when you consider energy emitted at frequency much larger than the critical frequency, you have a square root of the argument times which is cut off by an exponential, a negative exponential. So let's have a look at what this function looks like. I show here two plots. The one on the left is just linear scale, linear in both axes. So you clearly see this is units. The x-axis is unit of frequency over critical frequency. So you see that you have a peak just around 0.3 critical frequency. So you see that most of the power is indeed emitted around the critical frequency, more or less, a fraction of the critical frequency, but that's the point. If you look at the right plot, you see that the very same plot in a log-log scale. So particularly when you are interested in comparing the energy emitted at different decades along frequency, you see that the decade which takes most of the energy is the decade of the critical frequency, so the decade of when the argument is around 1. And in particular, you see here at very low frequency, this looks like a straight line. I remind you, a straight line in a log-log plot is a power law. And indeed, the slope here is 1/3. So this is the spectrum of one single electron. And finally, you now see proven the second statement that I made about the properties of the distinctive properties of synchrotron emission. So the spectrum becomes continuous. This is a continuous spectrum. And second point, most of the energy is emitted around the critical frequency. So that's why it's very important to know. Now you appreciate the role, the importance of critical frequency, because it tells you where the frequency range at which most of the energy is emitted, and so the frequency of the photons that are mostly produced. So an electron emitting synchrotron frequency will emit photons of any, in principle, of any possible frequency, but most of them will have a frequency comparable with the critical frequency. So when you make naive calculations or counts or some very basic considerations, you can assume that for a given electron with a given Lorentz factor, to a given Lorentz factor, it corresponds a given critical frequency. So you can very roughly assume that most of the photons emitted by synchrotron radiation by that given specific electron will have a frequency around the critical frequency. So by now you should appreciate the crucial central role and meaning of the critical frequency. Of course, we have to remind ourselves about the assumption that we've made. We assumed that the energy, if you remember, lost by one single loop around or orbit around the magnetic field lines is negligible with respect to its energy. So let's consider first of all the first case of non-relativistic electrons, so in which instead of synchrotron radiation we are dealing with cyclotron radiation. That means that if you emit we saw that the typical frequency is just the cyclotron frequency. So what we call nu or omega. Okay, when I keep saying omega as frequency, but of course it's an angular frequency. So nu L is the corresponding. So QB over 2 pi MC times h. It has to be, of course, much smaller than the rest energy of the particle. But if you replace, as I said, instead of if you use the formula definition of cyclotron frequency, you can set this as you see that the only possible variable is just the magnetic field, having fixed, for example, the particle, so the electron. So it means that this, in the case of cyclotron frequency, this approximation holds true as long as the magnetic field is smaller than 10 to 13 Gauss. So otherwise, when this is no more the case, it means that quantum effects can no more be neglected. So you cannot stick anymore to a classical description, and what shows up are the so-called quantized orbits, Landau levels. So you have to take into account the discreteness of the emission through a quantum approach. This is something we are not going to do that. Instead, in the case of synchrotron radiation, so getting back to the relativistic case, of course, you have to make sure that the power emitted during one orbit, so P is the total power of synchrotron radiation times what? Well, times the period of one single orbit. which is just 2 pi over the cyclotron frequency, has to be smaller than the rest energy, well, not the rest energy, the total energy of the electron, which is in this case, of course, is gamma times its rest energy. But just using the formula, one of the earliest formula we've come up with today. So the total power, and of course the definition of cyclotron, of gyration, sorry, frequency, so which is the cyclotron frequency over gamma, has to be smaller than this. Again, if you calculate here, there's b squared over b, so you're left with b, and then there is gamma cube, and with gamma, I mean, it's straightforward to see this is equivalent to have this condition. But you can express, as we did in the previous case, you can turn this condition on a condition for the magnetic field. So this holds true as long as the magnetic field is smaller than this value, which, so replacing the constants here, you see 10 to 15 Gauss over gamma squared and the pitch angle, the sine square of the pitch angle. But you can also, for example, use this condition as a condition on the Lorentz factor of the electron, having for a given magnetic field. So, for example, if you just invert the magnetic field, you bring the magnetic field here and the gamma here. Let's assume, for simplicity, a pitch angle comparable with 90 degrees, so sine is just 1. So it means that, for example, for a given b, the Lorentz factor has to be smaller than this value, which means, for example, smaller than 40 for a magnetic field as the one we've seen for a Newton star, as the one we considered, which in terms of total energy of an electron, if you think of an electron, means that as long as you have electrons with energy smaller than 20 MeV for this kind of magnetic field. Of course, the weaker the magnetic field and the correspondingly higher the electron's energy can be. So far, let's recap what we've come up with so far. So what we studied is the energy, the total energy, so the total power emitted by a relativistic electron, as well as its spectrum. And we saw that one single electron gives birth to a continuous spectrum, which peaks at the frequency, at the so-called critical frequency, which scales with gamma squared. Okay, fair enough. But now let's move as much in the same way as we did for the Bremsstrahlung case. You remember we first studied the emission properties of one single electron, and then we moved to consider realistic populations. In that case was a thermal population. Now, synchrotron radiation is often due to, well, is ultra-relativistic electrons. And especially in astrophysics, such a population of ultra-relativistic electrons is often found as the result of some mechanism which is very effective in accelerating all these electrons to high energies. We will see an example towards the end of this course, particularly through shocks, for example. Shocks are very effective tools to accelerate particles to very high energies. And you might wonder, what's the final distribution of the electron's energy? Is that a thermal distribution? Well, the answer is power law. So it is often the case that when you wonder the total power emitted by a population of electrons within a magnetic field, well, given that these electrons are emitting synchrotron means that they are ultra-relativistic, but a population of ultra-relativistic electrons is often, as I said, found to be the case for a power law distribution. So the goal now is to find out what's the total resulting synchrotron radiation of a population of electrons whose energy is described by the power law distribution. So power law distribution, it means, for example, that you have an index of this power law, which in the literature is used as p, particularly minus p, where p is meant to be a positive number. And which means that, of course, the more energetic electrons you think of, and the fewer. How few? Well, that's exactly described in this distribution. And what is this? This holds, of course, this it cannot hold for an infinitely large range of Lorentz factors, but it will be the case between two boundary values, one gamma 1 and one gamma 2. So within this range, you have a population of electrons whose Lorentz factor is described by this. How many of them is told you by this function. And of course, you know that I keep saying electron energy distribution, but speaking of energy or speaking of Lorentz factor is fully equivalent, because of course energy of a relativistic particle is just gamma times its rest energy. So the unit of measure of C in this case is just 1 over volume. Why? Because by definition of the distribution, if you calculate dn as this function here and times d gamma, this value here is the number of electrons per unit volume having Lorentz factor between gamma and gamma plus d gamma. So this is the meaning of the distribution. So this dn is the total number, well, the number of electrons per unit volume, and that explains why C has the units of 1 over volume, in such a way that n times dn is the total number per unit volume of electrons having Lorentz factor between gamma and gamma plus d gamma. Now, what I'm gonna show you is this result. So, is the resulting total power, the synchrotron power, due to this power law distribution of population, power law distributed population of electrons, is also a power law spectrum with an index S. And I show S must somehow depend on P. You change P and you change automatically S. We'll see in a moment, we'll derive the formula for S. So let's see from a qualitative point of view what I am expected to do. Well, of course, the resulting spectrum, you have to integrate the power of each electron times how many of them you have. So how many you have of them is just n gamma times d gamma. N gamma is C gamma to the minus P d gamma. And of course, P as a function of omega, I remind you that this has in itself a dependence on gamma. So that's why you cannot take it out of the integral. In particular, let's remind ourselves that P is a function of capital S with some proportionality constant. That's why I use here the proportional symbol instead of equal. I don't care about the numerical coefficients. I just want to recover how the total power scales with frequency. So here, omega over omega c. But I remind you, omega c is a function of gamma. In particular, let's define this adimensional new variable as x as omega over omega c. But omega c scales with gamma squared. So if I want, I have to make it explicit the dependence of x on gamma. And in particular, I also put the dependence on b. It's a useful outcome. Here I also put b because b, if you get back to the power formula, you see that there's also dependence on b like this. Now, it's just a matter of working out. You see, you are calculating this integral, changing variable, moving from gamma to x. Very, very simple things, just an exercise for kids. So if you invert, gamma is the square root of, you work out the differential. So you see that you gain x is to minus 1/2, so minus 3/2. And well, the rest is just the same, apart from a factor of 2 here. So now let's work out the integral. You see, you have to replace gamma to the minus p, but gamma is this guy here. So you have omega to minus omega to 1/2 and to minus p, so omega to minus p/2, this guy here, minus p/2. But then you also have from the differential here, d gamma, sorry. So you have here omega to 1/2. So omega to 1/2 minus, you can express here minus 1/2. So the dependence on omega is this guy here. And then you have also the dependence on b, for example. You have here gamma minus p. Gamma is minus 1/2 minus p, so plus p over 2. And then you also have b minus 1/2 here, but you have here b1, so 1 minus 1/2 plus 1/2. So the total index of p is p plus 1 over 2. And then you see, you have an integral depending on just quantities which depend on x. The residual dependence on omega, of course, could be through the boundary terms of the integral. But provided that you, in many cases, many realistic cases, these can be considerably relatively large. So the integral, the dependence on omega is really smoothed out. So essentially, you can approximately assume that this integral no more depends on gamma, which means that the only dependence on omega. So the only dependence on omega is this guy here. And in particular, here we derive two very important pieces of information. So both the dependence on the magnetic field and the spectrum itself, so the dependence on frequency. And indeed here, not only did I prove that the dependence on frequency is indeed in a power law fashion, in a power law-like fashion. Indeed, you see, this is a power law. But we also obtained the formula for the power law index of the spectrum, what I called at the beginning S. So S is indeed p minus 1 over 2. So if you know the power law distribution of your population of electrons, you automatically know the power law index of the resulting spectrum. You start from a power law, you end up with a power law. Of course, they live into different spaces. Of course, this is the power law describing the distribution of the energy of the electrons. This is the power of the resultant spectrum. So you know P, you automatically know S. But you see, it's also interesting because what you measure, as a matter of fact, are always spectra. So if you manage to measure the spectra, it means that you can experimentally, from an observational point of view, you can measure S. But if you measure S and you have reasons to believe that this is indeed synchrotron frequency, you can measure automatically the energy distribution of the population of the electrons. Really powerful. Not only, but you also recover the dependence on the scaling with the magnetic field. So by changing the magnetic field, and that means you can also somehow constrain the magnetic field intensity. So if you carry out the detailed calculation, so taking into account the capital F function that you remember I defined as a modified Bessel function, so really boring and from a purely mathematical point of view, but so you carry out the same calculations, you replace exactly the value for P, so you have all these terms. In particular, if you work out instead of F the integral using, as I said, the exact formula, you end up with this pretty scary expression. Don't be scared. Just sorry about that. What is important here, the capital gamma, is the gamma function, and which of course depends on P, because we are talking now about the population of electrons. So you see that what is mostly important here is the dependence on omega. You see that's exactly minus, so what we call S is just P minus 1 over 2, as well as B. B gets here and here, so the total combination is P plus 1 over 2. There's this mind. This still depends on alpha, on the pitch angle. So this means that this formula applies for a population of electrons with whose energy distribution is described by P, but all having the same pitch angle. If you move on and you wonder, much in the same way as we did when we calculated with the Larmor's formula, if you assume instead a population of electrons whose velocities are isotropically distributed, so it means that the pitch angle is equally probable for any possible value. Well, again, in this case, the calculation is more complicated because you see that the sign of the pitch angle is also gets through a Pauli dependence on P. So using this result, which of course I'm not going to prove, so the average, this integral depending on P, on the P power is just this combination of gamma functions, you end up with this result. So this is the same guy averaged out for an isotropic population of electrons. Okay, so of course the dependence, the scaling with omega and B is completely unaffected, so it's the same as before. I use different colors to highlight what you see here in colored with colors. It means that that's the most important things to remember. The rest, of course, it would be crazy. I don't remember. It's of no use to remember this. So indeed, that's the scaling is important to remember, especially if you have to remember just one of the two. This guy here, the dependence of this is important. I would like you to remember this. So for a population of electrons with index P, the spectrum is a power law with index P minus 1/2. That's it. It's instructive to think from a qualitative point of view how from this panel here, the top panel here, which is the spectrum of one single electron, how you can end up from this guy to this guy here. Well, a power law distributed population of electrons, it means that each electron, if you think each electron has its own critical frequency, the lower the Lorentz factor, and the correspondingly lower by a factor of gamma square will be the critical frequency. The critical frequency is the frequency at which the spectrum peaks, the spectrum of one single electron. But if you think of the distribution of electrons, it means that the lower the Lorentz factor, the more electrons you have. Remember, gamma minus P. So it means that when you sum up the contribution of this spectrum due to the individual electrons at lower frequency, you have many more. So that's why when you move to lower frequency, you have a correspondingly larger contribution. By summing up all this term in a log-log plot, you see that the sum here is a power law in this range. And that explains, at least from a qualitative point of view, why summing up a lot of this guy according to a power law, you end up again with a spectrum which is a power law. And so far we talk about the emission processes. What about the absorption? Well, for the very same reason that I told you repeatedly, once you consider a process which is capable of emitting radiation, the same process can also work in the other way around, so in absorbing. Here it's called synchrotron self-absorption. What does this mean? Well, for example, look at this drawing here. It means that you have an electron which at some point creates a photon because it's emitting through synchrotron. So you have a photon which was generated by synchrotron emission, which is then absorbed by another electron, which will be then emitting a more energetic photon. So it absorbs this one and then keeps emitting another one. So self-absorption, because the synchrotron is both responsible for the creation of photons and for absorption of them. To investigate synchrotron self-absorption, what I wrote here is something which you should realize if you understood radiative transfer. Now, think of the population of the electron. You know we know J nu, so we know the power, so we know the emission coefficient. This is what kept us busy so far. We want to calculate alpha, the correspondence. Do we know the source function? The answer is no, we don't. Why? Well, the population of electrons is by no means thermal. We have a power law distribution, which means you cannot apply Kirchhoff's law. So you don't know, in principle, the source function. So you cannot exploit the same trick that we did when we were dealing with thermal Bremsstrahlung. The magic word thermal here is not available. So to do things properly, you have to go back to a more fundamental level. You have to obtain Einstein coefficients and do what I reminded you about many cases. This is not what we are going to do. It would take us too far away. But if you're interested in this, you can have a look, for example, at the Rybicki-Leitman, which provides you with a very full detailed treatment. What instead here we want to make is to obtain the scaling of alpha, so the scaling of the absorption index, the absorption coefficients, in particular on the magnetic field intensity and on frequency. To do this, we use a trick. And the trick is this. We assume that, of course, the population of electron is by no way a Maxwellian. It's a power law. But we can think of this power law as the results of a superposition of many different Maxwellians, and having in mind each of these Maxwellian distribution, of course, you can associate a temperature. So we can think of any single electron having a specific gamma to be associated with a single Maxwellian. In which sense? Well, you know that each single electron is emitted in a continuous way, as a continuous spectrum, but there's a special frequency at which most of its energy will be emitted, which is the critical frequency. So we can kind of associate that any photon emitted at the generic frequency nu is due to the emission of an electron whose critical frequency just equals that generic frequency. So if you think, okay, I'm thinking of a frequency of energy emitted at the frequency nu, well, you can think of the corresponding critical frequency nu c. So you can think of a critical frequency which is just equals that frequency. So you automatically associate to a given frequency a given electron. But the given electron is associated to its corresponding Maxwellian. So you find a trick to associate to a given frequency a given temperature. And how this? Well, if kT is of the order of the energy of our hypothetical electron, well, that has to be equal to the total energy of the electron. But the Lorentz factor of the electron, I remind you that critical frequency scales with gamma squared. So gamma scales with square root of the critical frequency, in particular with the square root of the critical frequency over the lemma frequency. But you see, when the source is absorbed, it means that you are in a kind of thinking of, since we have turned the problem into a composition of Maxwellian distributions. So we sort of recovered a thermal analog. But in the absorbed case of a thermal analog, we know that the spectrum works like in the Rayleigh-Jeans regime, where TB is the brightness temperature. So the intensity is now scaling with nu cube with TB. But mind, in this case, in this very case we are considering, the temperature itself depends on gamma, because we are associating to any given electron or given temperature. But indeed, so the temperature itself is, through this line of reasons that we carried out this way, the temperature, brightness temperature, is associated to gamma, which is in turn associated to its corresponding critical frequency. So it means that kT scales with the square root of nu. But combining this into all this, you see that the total scaling is with gamma to the fifth to the 5/2 power. And here I also included the dependence on B. Yes, because the dependence on B goes through the dependence on the Larmor. Exactly, gamma scales for a fixed frequency, critical frequency scales with 1 over square root of B. So this is indeed. So somehow you see, I recovered the scaling of I, the intensity, in the absorbed regime. So when the optical depth is much larger than 1, using this trick, the assumption that I exploited above holds true as long as I wrote here, at any frequency, you can think of a corresponding electron whose critical frequency equals that frequency. Well, but if you remember the distribution of electrons, I said, oh, let's assume there's gamma 1 and gamma 2, which are the boundaries which define the distribution of Lorentz factor for a given population. So gamma 1 is gamma min, is the minimum Lorentz factor available for your. When this trick holds no more, if you consider very low frequencies, so low that its corresponding Lorentz factor is below gamma min, well, it means that this trick holds anymore. So kT is no longer depends on gamma or nu, but it just depends on nu of the lowest of the least energetic electrons. So it means that in this case, there is no extra scaling with nu, and just I would scale with nu squared, just like that. So it depends on the range of frequencies. But the point here now is, since we calculated I, intensity, specific intensity, in the optically thick regime, assuming a number of Maxwellians, but nevertheless, we calculated I in the optically thick regime, but we know from radiative transfer, I in the optically thick regime is the source function. So now we use this trick to infer the scaling of the source function on both B, magnetic field, and frequency. So now we can, as a consequence, recover the scalings of the absorption coefficients on the same two quantities. In particular, here, J nu, so the power we calculated in the previous slide, so with the scaling, which I'm not going to repeat, over the scaling we just obtained, so you end up with the scaling as a consequence of the absorption coefficient on both magnetic field and frequency. As I said, if you want to see the full detailed treatment, you have to go through Einstein coefficients. Please refer to some textbook that I mentioned. But this is instructive. This is a trick which surprisingly works pretty well. You started with a non-thermal distribution, but you exploiting the properties of the synchrotron radiation that you can associate to each given frequency, a given Lorentz factor of the electron. We just use this trick. So the spectrum, the overall spectrum of radiation, again, when you consider the two optical depth possible, you see that when in the optically thin regime, So I remind you, we are still considering a powerless distributed population of electrons, okay? So in the optically thin regime here, it is a power law with index p minus 1 over 2. And in the optically thick regime, it is this guy here. It's a power law with index 5 over 2. And unless you move to very low frequency, when self-absorption comes into play, so when you go to a frequency in which you go below the minimum frequency corresponding to the minimum Lorentz factor of the population of electrons, in which the slope changes is 2. So of course the peak, if you measure the peak, it means that you can measure where the frequency at which alpha times the size of the source is 1. But you see, if you combine the knowledge of the spectrum here with measuring the frequency here, you can constrain both P and the magnetic field itself. So this is a way, from purely a spectrum, you can constrain the magnetic field in which electrons are emitting. As I said here, of course, I'm not going to prove this scary formula here, but it's just for your information. This is what a detailed calculation gives you. And okay, this is called self-absorption frequency, just because it's the frequency at which you change regime. You move from an optically thin, optically thick, or the other way around, depending on whether you are decreasing or increasing frequency. Okay, this is just the total formula. Again, if you work out the same exercise, this matches in the same way as we did for the emission coefficient. So for the power emitted, in this case, this holds for a specific pitch angle. If you average for an isotropic distribution, you end up with this even scarier formula. But don't be scared. Don't panic. There's nothing to get worried about. The dependence, the scaling on B, and in particular on frequency, is just the same. This is a slide which is just meant to provide you with a useful, very handy formulae. So here I summarized the emission coefficient. Before, we just talked in terms of total power as a function of the angular frequency. If you do things properly, J nu, so the very definition of specific coefficient of the emission coefficient is a function of nu. You have to consider that this is just, you have to divide by the solid angle for pi, and just remember the factor of 2 pi when moving from omega to nu. So you see that this is just a factor of 2. So this is the formula, the general formula for the emission of a population of electron in the isotropic distribution. So it has already been averaged out for the pitch angle. And this is the corresponding formula for the absorption coefficient. Here you see there is a coefficient alpha as a function of P and B, A as a function of P and B as a function of P. These are numerical coefficients as a function of P. And here I put this table. I just put the very typical values of P with the corresponding values of the corresponding coefficient. So this is a very practical formula. You have a distribution of a population of a powerfully distributed population of electrons, isotropically distributed. You need to calculate both sink emission and absorption. This is what fits your needs. With this, if you want to calculate if you want to understand where these coefficients come from, this is just the exact definition. You can also have a look at the chapter 4 of Ghisolini textbooks. Instead of using these numerical coefficients, it gives you some very approximated formulae, which is also very useful. If you want you see a lot of constants here, the charge of the electron, mc squared, and blah, blah, blah. You can, if you think of electron, it means that you can immediately replace the value of the charge of the electron with the mass and everything. And in Gaussian units, you have this very handy stuff. Gaussian units, it means that nu is meant to be in units of Hertz, b in units of Gauss, c in units of centimeter to minus 3, and the rest is just here. And the result, of course, for the J nu is just Hertz per cubic centimeter per Hertz per second per steradian, and the same here, where, of course, the unit is centimeter to minus 1. So should you work out, these are just very easy, very practical. And again, okay, this is just another figure showing you the total case of a typical optically thin and optically thick here, thin here. So if you measure the transition, the self-absorption frequency, as I said, you can measure B, for example. So you measure both P and B, the magnetic field. So you see, when you measure a spectrum and you identify this guy here, you have a straight. Let me finish this class showing you a very beautiful example of, in astrophysical example of synchrotron emission. This is our own galaxy, you see, as seen in the radio band. Here the central frequency is around 400 megahertz. This is a color-coded image, so the bluer, the more intense the radio flux. This is the plane here, the horizontal plane is the plane of our galaxy, okay? So this is a galactic coordinate. So you see that there is clearly an emission, so all this bluish part is clearly due to what lies within the galaxy. Now, we know that this galaxy, we know that our galaxy is filled up with a magnetic field whose average intensity is of the order of 1 microgauss, so 10 to minus 6 Gauss. And this is very typical of other similar galaxies. So this is very typical galactic value of the magnetic field. Now, and we had many ways to measure it, but I'm not going to say that how we did this. But in this case, for example, you can immediately estimate the typical energy of the electrons which are contributing this synchrotron emission. We know that this is synchrotron emission for the spectral properties. And you see, you are receiving energy at a frequency around 400 megahertz. But this has to be the frequency, the critical frequency of given electrons. So you calculate, you know B, you know the intensity of the magnetic field. You know the critical frequency, so you have all the ingredients to work out the Lorentz factor of the electrons, which are responsible for this synchrotron emission. And this is really bright. You see, if you use a radio telescope at this frequency, you see really strong synchrotron emission. These are electrons that are moving within our own galaxy and being entrained in a region filled up with a magnetic field, they automatically emit synchrotron emission. So you immediately estimate the Lorentz factor of these electrons, and you see that you come up with a Lorentz factor 10 to 4. So there are sources in our galaxy which can accelerate electrons to really hugely relativistic energies, 10 to 4, a Lorentz factor of 10,000, really incredible. And we will see that there are sources which are capable, even in our own galaxies, of accelerating electrons to much higher and incredible 10 to 8, 10 to 9, something mind-boggling. And I think I'll stop here for today. I already said a lot of things. So I think you have a lot of stuff to think about before next class that will be next Monday. So do you have any questions? Okay, I stop the recording.